Hi, everybody. In this video, we're going to talk about this spreadsheet or workbook, Mantle TP Calcs, followed by a date that indicates whatever the latest version is. And I'm going to break this up into a couple of videos because there's just a lot going on in the workbook. And so what we're going to do is we're going to start out in this video just talking about data entry. What are the inputs and where do they go? And then in other videos, we'll look at some of the behind the scenes stuff with the calculations and how you can edit and customize the spreadsheet. So there are two sheets here where you can input data. I'm starting with Calc P iterative, but we also have an input P. We'll take a look at that in a moment. It's set up pretty much the same way. Let's go back to Calc P iterative. So here, the inputs are a liquid composition, and you would enter those compositions here. These are all in weight percent values. Iron is as FeOT, FeO total. We are going to use an input oxygen fugacity to calculate the amount of ferric and ferrous iron, but when you start with a spreadsheet, you'll just input the iron as iron total, and then there is room to add water content here as well. By the way, in all of these spreadsheets, pretty much all of them, not just Mantle TP, gray is input and then blue is output. So output especially that you want to pay attention to that'll be of value. What are the other inputs here? Besides the liquid composition, we have an operative FO2. Now, if you think you know the operative FO2 is a log value, you can just enter that value here. But if you take a look up here, you'll see this is going to take cell E8. And it's just a fill down command for these. This will take cell E9, where it's referencing oxygen fugacity relative to the nickel-nickel oxide buffer. So the other input that you need to add is either a value here. Notice that this is nickel-nickel oxide plus Y. Y would be the number of log units above or below the nickel-nickel oxide buffer. So if you like nickel-nickel oxide buffer as a reference, and let's say you think you're at 1 log unit above nickel oxide, you could put a 1, hit return, and you could see all those values are changed by 1 unit since we're looking at log units. And then these values here, the operative FO2 would be a function of that cell there. If you like, let's say 1.5 log units below nickel oxide, you can hit minus 1.5. And now you're at 1.5 log units. If you want QFM as a buffer, quartz phthalate magnetite, you can make a simple edit. Instead of E8, you can make this equal to D8. So now we're grabbing this cell over here, and you can again change the value of X, so it's QFM plus X. The default is 0, so that means that the buffers are set to be right at QFM or nickel oxide, whichever you prefer. And then you can make it, 1 or 2 or whatever log units you like above or below. So that's the basic data entry. In here in gray, you're just putting a liquid composition and then an FO2. That's for Calc P iterative. You do not need to enter an olivine composition. In fact, you can't. It's not set up that way. Way over here to the right in column EV, we're going to predict the olivine composition, and we're going to use that predicted value as a way to test that we have a useful mantle potential temperature. Actually, we will talk about it right now, in fact. If you have a liquid here that is saturated in olivine, and it must be saturated, otherwise none of these models will work, we will estimate the composition of the olivine that liquid would be in equilibrium with. And you can check over in column AV, I think it was, not AV, AT, you can see what the predicted olivine composition is. And if that predicted olivine composition is something that you think is in your mantle source, then you're good. If the olivine composition is too low or too high, then that means you would have to find a different liquid composition, especially liquid with either lower or higher amounts of magnesium or iron, essentially a different iron-magnesium ratio, until you find something that would be in equilibrium with the expected forsterite value. So let's go to this final issue about P. In this Calc P iterative, you do not need to enter a pressure. We're going to calculate it from silica activity. The silica activity model is over here to the right in column AI, and that's going to give us this output pressure that's shown here in blue. And all of the calculations, the oxygen fugacity, the olivine liquid temperatures, and the mantle potential temperatures, that's probably the most important output for users of this spreadsheet. It's all going to be linked to that pressure there that is calculated through silica activity. If you don't like the silica activity models and you want to input your own pressure, you can go to input P. Everything here is exactly the same on this sheet over here. You would still input the liquid. All iron would be entered as iron total. It'll be recalculated elsewhere in the spreadsheet based on this operative log FO2, which is going to take these cells, nickel oxide by default. But here, notice that now column S, this pressure is in gray. So here you can enter the pressure in GPa to be anything you like. We take the silica activity calculation out of the iterative calculations. You enter the pressure that you like best, and then if you like the pressure, and if we migrate over here to column AT and you like the predicted forsterite content, and that means that your liquid composition is okay, then you have estimates for mantle potential temperature shown here in column Z and AA in the input pressure. And where are they? Also Z and AA in the Calc P iterative, and then you're more or less good to go. In the next couple of videos, we'll take a look at some of the behind-the-scenes stuff in terms of looking at melt fraction and the upward correction to account for the heat of fusion.